Hello, our group will present the topic 6 for fluid mechanics, momentum equation. This is our team members, Kelvin Diom, Chester Isaac, and Dion Nixon. And our lecturer is T.S. Abdul Sulaiman bin Ismail.
Before we start to answer the question, we must understand the definition of momentum equation. The fluid mechanics momentum equation is a mathematical statement of Newton's second law applied to fluid, which relates the net force acting on the fluid control volume to the rate of change of its momentum. It can be expressed as the sum of external forces, such as pressure, gravity, viscous forces, equals the rate of momentum change within the volume plus the net rate at which momentum flows in and out of the volume.
Question 3. A 400 millimeter diameter pipe carries water under a head of 40 meter with a velocity of 4.5 meter per second. If the axis of the pipe turns through 43 degrees, calculate the magnitude and the direction of the resultant force at the end.
For the solution, we have to collect the data we're given from the question. So the data we have is the diameters of the pipe at extremities of the bend, which is 400 millimeter, and we should convert to 0.4 meter. Next, we have velocity, which is 4.5 meter per second, and we have head, which is 40 meter, angle 43 degree, and we need to find the flow rate, pressure, force along x-axis, and force along y-axis.
Step 1. First, we will find the flow rate of the pipe. We will use the formula Q equals AV. Before we can calculate flow rate pipe, we must find the area of the pipe first. A equals pi 0.4 with the power of 2 divided by 4. The answer is 0.126. Now, we insert the area in the flow rate formula. Q equals, inside bracket, 0.126 times 4.50. The answer is 0.567 meter cube per second.
Step 2. To find the pressure intensity, we use the formula P equals to PGH, where P is density, J is the acceleration due to gravity, and H is the head of the fluid column. By substituting the value 1000 for density, 9.81 for gravity, and 40 for head, the pressure becomes 392,000. Next, we convert the pressure from Pascal to kilopascal by dividing by 1000. So, 392,000 divided 1000 equals to the 392 and 410.
After we found the value for flow rate and pressure, we can continue to calculate the force along x-axis and y-axis. For the formula of general momentum equation, we need to calculate rho q times v1 minus v2 cos theta plus p1a1 minus p2a2. The term of rho q times v1 minus v2 represents the change in momentum flow. Meanwhile, the term of p1a1 minus p2a2 represents the net force due to pressure. Our goal is to apply this vector equation in both the x and y directions. To find fx, we must put the general formula, then add cos theta behind v2 and a2. After that, calculate the value of fx. So, the final answer for fx is 698.734 kN. Meanwhile, to find fy, we just change the cos theta to sin theta in the formula, then calculate the value of fy. The final answer for Fy is minus 1773.84 kN.
For the last step, the resultant force is calculated by combining the vertical and horizontal component. The vertical component is 698 and 7300, and the horizontal component is 1773 73 and 84 hundredths. When the components are combined, the magnitude of the resultant force is 1906 and 5 tenths. Next, the direction of the resultant force is found using the tangential. The angle is calculated by tan A equals to Fy divided Fx, where Fy is 1773 and Fy is 698 and 7300. We will get 2 and 530 times 1000. Taking the inverse tangent of 2 and 539,000 gives alpha equals to 68.5.